This section is called an overview of trending methods. So there are a number of different trending methods that forecasters can use to create their trends. The key ones that we think are useful have been coded into the OI prediction engine, which is the source of a different tutorial. This tutorial will actually explain the trending methods in a little bit more detail and talk about how to pick or choose between them. So there are certain reasons that somebody would pick one trending method over another one. One is trending theory. Two is just experience with the methods, personal experience. Three is knowledge of the market. For example, if there's a lot of seasonality in the market, then you'd want to pick a seasonal method. If there's no seasonality in the market, you don't want to pick a seasonal method. Fourth, you can actually look at the fit of the model to the historical data. Generally, the better the model fits the historical data, the better the model's working, but not always. The real gold standard is what's listed last on this slide, which is empirical testing of trends compared to held out data. So what you do is you take some of the historical data, the most recent historical data, and you take it out of the data set, and then you trend using the data minus the held out data. So you get your trend, and then you compare it to the held out data and see how well you did. And obviously if your method is trending very close to the held out historical data, you have a lot of confidence that you've got a good method. So the list of trending methods that we'd like to talk about here are linear regression, moving averages, exponential smoothing, that includes the prominent types of simple, Holt, and Winters, Box-Jenkins, nearest neighbor smoothing, and polynomials. So linear regression. Linear regression is a method to fit a line to some data such that the sum of the squares is minimized. And once we do that, then we continue that line out into the future, and that continued line is our trend. And this really reflects what you do with your eye. This is how people often see if something's going up or down. And Excel has this as a built-in function. But it's got a fundamental problem, which is what period to use. So here's mathematically how a linear regression line is calculated. So again, you construct a line through the historical data such that the sum of the squares of the distances between the data and the line are minimized. So you minimize the sum of the historical data minus the line, each one of those squared. Graphically, here's what we're doing. So the dark blue line is the historical data, and the kind of pink line is our linear trend. And you can see, at least on the left-hand side of the graph, we have these light gray lines, vertical lines, drawn between the pink line and the blue line. These are the differences between the historical data and the linear line. And so what we do is we take the distance of each data point, each vertical gray line, we measure it and then we square it. And then we take the next one, square it, and add it to the first one. And then we take the next one, square it, and add it to the first two. And then we add all of those up all the way through the whole period. And then we use some kind of an optimization program to minimize the sum of the squares. But as mentioned earlier, we have a fundamental problem of which historical data period to use. So here we have the same historical data as represented by the dark blue line. And if we took just the first, maybe third of the data, our linear regression would be the dashed pink line going way up, as we go out into the future. If we take the middle third of the data, we get the linear regression number 2, which is the dashed green line, which is relatively flat, declining a little bit. If we take the last third of the data, we get linear regression number 3, which is the light blue dashed line, which is declining pretty rapidly. And then if we take the whole data set, we get linear regression number 4, which is represented by the maroon dashed line, which is lower than the green dashed line, but it's kind of headed in the same direction. So all of these are perfectly legitimate representations of the historical data. The question is, which part of the historical data do you think is most important? Is it the beginning part, the middle part, the ending part, or the whole thing? And you as a forecaster have to decide that, because you have to pick what data you want to use to create the linear regression. Okay, let's move on to moving averages. Moving averages are averages that are updated as new information is received. Moving averages have some pretty significant shortcomings. One is that it dampens any upward or downward sloped trend. 2 is that it shifts peaks and valleys. And 3 is it really can't be used for extrapolating. It's just for smoothing only. And so here mathematically is how moving averages are calculated. And essentially what we're doing is we create an average for the last n data values. And so, for example, a 3-month moving average, so the moving average in period I would be the data, the historical data in period I, plus the historical data in period I minus 1, the previous one, plus the historical data in I minus 2, the previous period. And then you just take the whole thing and divide by 3. So here, this next slide is a graphical representation of moving averages. So again, we have the same historical data. It's the solid blue line. If we take a 3-month moving average, we get the pink dashed line. If we take a 6-month moving average, we get the black dashed line. And if we take a 12-month moving average, we get the light blue dashed line. And so the forecaster actually needs to decide how many months to average. And you can see that the moving average is actually very different depending on whether we use 3, 6, or 12 months or something else. But you'll also notice that the peak is shifted to the right with the 12-month moving average compared to the actual historical data. And it also dampens any upward or downward slope trend. And then further, we cannot use it for forecasting, for trending, because there's no mechanism for taking this out into the future. The next technique we want to talk about is exponential smoothing. And exponential smoothing is actually really interesting because it's similar to linear regression, but you can think of it as the most recent data points are weighted more heavily. The other thing to know about exponential smoothing is generally it's the best overall technique, and it's the technique that we focus in on in the short-term forecaster model. So with exponential smoothing, there are a number of different models, but there are 3 primary ones. There's simple exponential smoothing, which is 1 parameter, Holt exponential smoothing, which is 2 parameters, Winter's exponential smoothing, which is 3 parameters. And like linear regression, what we do is we calculate the sum of the squared errors over the historical data, and we optimize the model to minimize that sum. So it's actually very similar to linear regression, but we get a very different result. So here's the first example, and it's using simple exponential smoothing, which is 1 parameter. And with that 1 parameter, all we get is the level. So you can see the blue line is the historical data. The red dashed line is the model we've created. And then the green solid line is the trend. And so the trend has no slope and it has no seasonality. All we get is a level right at 80,000 vials. So you can see that the trend is flat. Now with our next example, we're going to look at a 2 parameter exponential smoothing model, also called Holt. So here we have the same historical data. The model we've optimized here is the red dashed line, and then our trend is the green solid line. And here you can see that it has a level and it has a slope. So it's downward sloping out in the future. It actually looks like a pretty good trend. And our final example is Winters, which is a 3-parameter exponential smoothing, and it includes seasonality. So to represent the seasonality, we have different historical data here, which is the kind of brownish data on the left hand of the graph, and then our trend is the blue dashed line on the right hand side. So you can see that our forecast actually captured the peaks and the valleys, the seasonal peaks and the valleys in the historical data. So I just want to read this quote from Robert Goodrich out of a forecasting book. Exponential smoothing techniques are among the most widely used in the world. They're easy to use, surprisingly accurate, and easy to understand conceptually. Little effort is required to fit a model, and less historical data is required than with correlational models. Furthermore, exponential smoothing models are both robust and adaptive to changes in the structure of data. So what he's really saying is that exponential smoothing models just have so many advantages that they're typically the go-to trending approach, trending method. Next, let's talk about Box-Jenkins. So Box-Jenkins is good in situations where there's lots of historical data, and it's good for handling complex time series. And it's also good when the underlying structure of the data is understood, and it's using an ARIMA method. And essentially what Box-Jenkins does is it builds the most parsimonious model that reproduces the autocorrelation function of the data adequately. And there's a lot packed into that sentence that we'll leave that for a deeper explanation of the models. But let's just go with that for right now. Okay, on to the next method, nearest neighbor smoothing. So nearest neighbor smoothing is similar to moving averages, except that it's got some real advantages. One is that it doesn't change the level of the data, and it also doesn't move the peaks and the valleys. So if you typically have a peak, say in the spring, and a valley in the fall, when you apply nearest neighbor smoothing, you're still going to have your peak in the spring and the valley in the fall. And all it does is it averages the values around the value you're considering. So here's the formula. Nearest neighbor value I equals the historical data for the previous month plus the historical data for the current month plus the historical data for the next month, all three of those divided by 3. And you can smooth as many times as you want. So then you can iterate on the formula. So you can just smooth the nearest neighbor smoothing results and do it again and again and again. You can do it 1, 2, 3, 4, 10 times. But like moving averages, it's a smoothing technique, not a trend generation technique. And here graphically is what's going on. So the dark blue line is the historical data. And when we smooth it 3 times, we get this light blue line. And when we smooth it 20 times, we get this reddish line. So you can see that the peaks and the valleys are still in their original places. And the way to think of this is it's eroding the peaks and filling in the valleys. So the overall levels don't change. So you could take an average of all the points in this graph, and the average would be the same for the historical data and the smooth 20 times and smooth 3 times. But what it does is it gets rid of what you can think of as noise, and then you can look at more of the underlying structure of the data. Okay, the last method that we're going to cover today is polynomials. And with polynomials, what we do is we try to understand the underlying form of the data. And there are many different forms of polynomials we can use. Some use sines and cosines, some use x's and x squareds. And what we do is we fit the model within the historical period by optimizing the coefficients. So again, like linear regression, we're minimizing the sum of the squared errors over the historical data. Polynomials can be great for trending, but they can also be dangerous because of nonlinearity. So within the period where you have historical data, you might get a very well-behaved model. But then as soon as you go, a couple months into the future, you can just get a model that kind of goes out of control, and your trend just goes either through the roof or through the floor. Okay, so in summary, we have a number of models we can use. One is moving averages. The other is linear regression, fits a line to a set of data. But again, we have to pick which historical period to use. Exponential regression, which we didn't specifically talk about, but it provides a trend that grows exponentially. And then we have different polynomials. We talked about that. We also have Box-Jenkins models that build the most parsimonious model that reproduce the autocorrelation function of the data adequately. And then we essentially have our star, which is exponential smoothing, which provides a trend like linear regression, but it emphasizes the more recent data points more heavily, and we don't have to worry about which historical period to use. And then finally, something we didn't talk about is with exponential smoothing, for Holt and Winters, we can actually dampen the trend. And so what it does is it attenuates the slope over time, leading to a flattening trend. So if the product is growing, that growth will gradually flatten. And if the product is declining, that decline will gradually flatten. Okay, that's it for this tutorial. Thank you.